Hello, in this video we're going to solve the cooling tower problem. In the last video we found the change in the mole fraction of the water vapor, the change in the temperature of the water, and the change in the temperature of the gas with respect to its position in the cooling tower. So in this problem we're going to code it out. In this video we're going to code it out. We're going to solve the differential equations that we derived in the last video for a 20-meter tall cooling tower where the air-water heat transfer coefficient is 10 watts meter squared per Kelvin. The specific area of 5 meters cubed per meter squared per meter cubed. The hot water enters from the top at 70 degrees Celsius with a flow rate of 0.5 kilograms per meters per second. Air enters from the bottom with a velocity of 5 meters per second and at a temperature and relative humidity of 25 Celsius and 50% respectively. And in this Python video, we're going to be making plots of the water temperature, air temperature, and the water partial pressure as a function of the position in the cooling tower. So let's get right to it. So I already went ahead and wrote down all the variables and that we needed. We needed the heat transfer coefficient, the gas constant, the density of air, the heat capacity of the air, the heat capacity of the water in the gas phase, the heat capacity of the water in the liquid phase, the heat of vaporization. I even got the mass transfer coefficient. It's equal to the heat transfer coefficient divided by the density of the air multiplied by the heat capacity of the air. We got the specific area, the molecular weight of water, the molecular weight of air, velocity, the liquid flow rate, and the pressure. And we have the height also of the cooling tower at 20 meters. We have the Antoine equation value for the saturation pressure for the water, and it will obtain the saturation pressure of water for that given temperature. We also have the importing of numpy as NP that will allow us to do numerical calculations, and we're going to also make some subplots, and we wanted to change the theme from light to dark, so we imported this. And from the integrate, we're going to solve some initial value problems. We're going to solve a root. And like I said about this, we made a function that will take the Antoine equation to find the pressure at any given temperature, right? Okay, so we're also going to add a few things and get started into the problem. So we're gonna name a variable z plot, and we want to take we want to call np.linspace, and we want the height. We want evenly spaced values from 0 to 21 with the height that we're gonna have. We're also gonna need the temperature of the water of the feed, and we know that 70 degrees Celsius plus 273.15, that will get us to Kelvin. We know if we change from temperature of the air of the feed, and that is equal to 25 plus 273.15. We need the mole fraction of the feed, and we can write that as the relative humidity multiplied by the function that we have for Antoine's equation, multiplied by the temperature of the air of the feed, multiplied by its velocity. That will give us the mole fraction of the feed. Okay, and we also need the gas flow rate of the air, and we know that's the pressure multiplied by the molecular weight of the air divided by the gas constant multiplied by the temperature of the air of the feed, and that is going to be multiplied by its velocity. We also running it. We also are going to need make some initial guesses for the mole fraction and the temperature of the gas of the stuff exiting the feed. So we're going to write y exit guess, and that is going to be the mole fraction of the feed multiplied by 1.1. We're just going to make a random guess of 1.1, and we're also going to be making a guess for the temperature of the gas of the feed, of leaving, and we're also going to multiply the temperature of the feed, of the air of the feed, plus 5. That's going to be a guess. And we want to place a placeholder for the solution for the sol variable, because later on we're going to use it. Okay, so now we need to solve our differential equations. So we're going to define a function. We're going to define the function dy twtg, and it's going to take in the height of the cooling tower, and it's going to take in the independent variable v. We're going to need to take an array. We're going to take an array of, it's going to start at the array of 1. The temperature of the water of the feed is going to start at an array of 1, 0, 0, 1, 2, yeah. 1, 2, yeah. The way counting in the array goes is this is 1 and this is 2. Temperature of the gas of the feed, and that's going to be V2. I'm going to clean this up a little bit and make it look nice. And what else we're going to need to solve this function to get the change in the mole fraction, the change in the temperature of the water, and the change in the temperature of the gas is we're going to need to define some certain equations. So we're going to need the gas flow rate of the water, and then that's going to be equal to the mole fraction divided by 1 minus the mole fraction of the water. We're going to multiply it by the gas of the air multiplied by the molecular weight of the water divided by the molecular weight of the air. We're also going to need the total gas flow rate, so we're going to do gas of the air plus gas of the water. We're also going to need the average molecular weight, and the equation for that is the gas flow rate of the air plus the gas flow rate of the water, and then that's going to be divided by the gas flow rate of the air divided by the molecular weight of the air plus the gas flow rate of the water divided by the molecular weight of the water. Run it, everything looks good. We're also going to need the heat. We're also going to need the heat capacity of the gas. We need to know the amount of water evaporating into the air. So, the heat capacity of the gas, the equation for that is the heat capacity of the air multiplied by the gas flow rate of the air plus what was I gonna think? Oh yeah, the heat capacity of the water in the gas phase multiplied by the gas flow rate of the water divided by the total gas flow rate. Oh wait. Yeah, I don't know why that went. Okay, so now in the last video we derived those three equations, and we also found the molar flux of the water, and we found that to be the mass transfer coefficient divided by the gas constant divided by the temperature of the gas multiplied by the pressure of the Antoine equation, and then we're also going to need the temperature of the we're also going to need the temperature of the water. Let's move that over there, minus the mole fraction of the water vapor multiplied by the total pressure. Okay, let's run it. Everything looks great. We're also going to need the three differential equations. So dy equals negative the specific area multiplied by the molecular weight divided by the glass flow rate multiplied by the molar mass of the water. We also have the change in the temperature of the water, and that's equal to the specific area divided by the liquid flow rate divided by the heat capacity of the water of the liquid. And we also need to multiply it by the what was the heat transfer? Yeah, the heat transfer coefficient. The heat transfer coefficient multiplied by the temperature of the gas minus the temperature of the water. And then I'm going to move this over here, subtract it by the heat of vaporization multiplied by its molar mass of water. So that looks great. Now we're also going to need one more equation for the change in the temperature of the gas. It would be the specific area multiplied by the heat transfer coefficient divided by the total gas flow rate divided by the heat capacity of the gas multiplied by the temperature of the gas minus the temperature of the gas minus the temperature of the water. Okay, looks good. And now we're going to return y dt w and dtg. We're going to return all three of those differential equations. Okay. And we don't know about the initial values. We don't know what they converge to, so we're going to make a function so we can know our exit values for the feed. So I'm going to tab all of this.